My dear students, welcome back to our channel. In this video, I will be explaining the BCA 5th semester subject Software Quality and Testing as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 3, first important short question is Test Case Design. Test case design means creating step-by-step instructions to check if software is working correctly. Think of it like checking a new mobile before buying it. You test the camera, battery, speaker, apps, etc. In the same way, testers create test cases to check each feature of the software. A test case usually includes Test Case ID. What to test? Steps to follow. Input. Expected result. Example. Suppose you are testing the login page of a college portal. Test Case ID TC001. What to test? Login with correct details. Steps. Enter correct username, enter correct password, click login. Expected result. User should successfully enter the dashboard. Good test case design helps find bugs early, saves time, and improves software quality. Tip to remember. Right steps plus right inputs is equal to right software. Next important short question is 2. Define defect. A defect is simply a mistake or problem in the software that makes it work differently from what it should. It is also called a bug. When software does not give the correct output or behaves unexpectedly, we say there is a defect. Example. Imagine you are using a mobile recharge app. You enter 100 rupee to recharge, but the app shows 10 rupees on the confirmation screen. This is a defect because the app is not showing the correct amount. Defects can happen due to coding mistakes, wrong requirements, or misunderstanding between the developer and customer. Testers find defects so that developers can fix them before the software is released. Remember like this. If software does something wrong, it's a defect. Finding defects early makes the software more reliable, user-friendly, and safe to use. Next, Unit 3. Long questions. First important long question is Testing as an engineering activity. Software testing is not just about clicking randomly on a computer screen or checking things casually. It is a proper engineering activity, just like constructing a building, designing a machine, or making an electronic device. Engineering always involves planning, tools, clear steps, and careful checking. In the same way, software testing follows a systematic and scientific process. Why testing is considered an engineering activity? 1. Clear requirements. Testers first understand what the software is supposed to do. Just like engineers study blueprints before construction, testers study requirements before testing. 2. Planning. Testers prepare a test plan which explains what to test, how to test, tools to use, and who will test. This makes the process organized. 3. Designing test cases. Test cases are like engineering designs. They describe exact steps, inputs, and expected results. This ensures repeatable and reliable testing. 4. Systematic execution. Testers follow each test case step by step, just like engineers follow their designs during production. This avoids mistakes. 5. Defect reporting. If something goes wrong, testers report defects with proper details. This helps developers understand and fix the issue quickly. 6. Verification and validation. Testing checks whether the software is built correctly, verification, and whether it gives what the user needs, validation. Real-life example. Think of manufacturing a car in a factory. Engineers test the brakes, mileage, safety features, horn, headlights, and engine performance. They follow strict procedures, tools, and safety checks. Similarly, when developing a mobile banking app, testers check login, balance display, money transfer, security, notifications, and more. Every check follows proper documentation and tools. Why this approach is important? Ensures high-quality software. Reduces chances of failure after release. Saves time and cost in the long run. Builds user trust and safety. Easy tip to remember. Testing is equal to engineering because it uses planning plus process plus precision. If engineers can't take shortcuts, testers also shouldn't because both build things people depend on. Next important long question is to explain in brief about testing fundamentals. Testing fundamentals. Testing fundamentals are the basic ideas and principles that help us understand what software testing is, why it is needed, and how it should be done. These fundamentals guide testers to find defects, improve quality, and make software reliable. 1. Testing shows presence of defects. Testing can prove that defects exist, not that the software is perfect. Example, like checking a bike before a trip, you may find problems, but you can't be 100% sure nothing will ever go wrong. 2. Exhaustive testing is impossible. We cannot test every possible input or action. So testers focus on important and risky areas. Example, you can't try all 1 million passwords, right? You test only the necessary conditions. 3. Testing should start early. Testing done early, during planning and designing, helps catch mistakes before they become bigger problems. Example, finding a spelling mistake in the blueprint is easier than fixing it after a building is made. 4. Defects cluster together. Most defects usually appear in a few modules. Example, in a mobile app, maximum bugs may be in the payment page rather than the settings page. 5. Pesticide paradox. If you run the same tests again and again, they stop finding new defects. So test cases must be updated regularly. Example, using the same pesticide on crops daily makes insects resistant. 6. Testing depends on context. Testing approach changes based on the type of software, banking app, game, hospital system, or e-commerce site. Example, testing again focuses on graphics, while a banking app focuses on security. 7. Absence of errors is a fallacy. Even if no defects are found during testing, the software may still fail if the requirements are wrong. Example, a perfectly built ATM machine is useless if it doesn't support local languages required by users. Easy tip to remember. FEEDPCA, the 7 fundamentals. Finding defects. Exhaustive impossible. Early testing. Defect clustering. Pesticide paradox. Context dependent. Absence of errors fallacy. These fundamentals help testers work smart, not just hard. Next important long question is 3. Discuss the strategies of black box test case design. Strategies of black box test case design. Black box testing means testing the software without looking at the internal code. You only check what the software does from the outside, just like a customer uses it. Testers give inputs, observe outputs, and check if the system behaves correctly. To design good black box test cases, several strategies, techniques are used. 1. Equivalence partitioning, EP. This technique divides input data into groups, partitions. If one value from a group works, others will also work. Example. If a form accepts age between 18 to 60, you can test with one valid value, 25. Invalid values, 10, below 18, 70, above 60. This reduces the number of test cases and saves time. 2. Boundary value analysis, BVA. Most errors happen at boundaries, limits, so testers check values at or near those limits. Example. For age 18 to 60, test 17, just below. 18, lower boundary. 19, just above. 59, just below upper limit. 60, upper boundary. 61, just above. 3. Decision table testing. Used when the output depends on multiple conditions. The table lists all combinations of inputs and corresponding outputs. Example. A loan is approved if salary 25,000 rupees. Good credit score. Decision table helps test each combination easily. 4. State transition testing. Useful when the system changes from one state to another based on user actions. Example. An ATM card can move through states like inserted PIN, entered options, menu, cash withdrawal, eject card. Test cases check each valid and invalid transition. 5. Use case testing. Focuses on how users interact with the system. It helps test real-life scenarios. Example. A shopping app use case may include login, select product, add to cart, payment, order confirmation. Easy tip to remember, EBDSU. E. Equivalence partitioning. B. Boundary value analysis. D. Decision table. S. State transition. U. Use case. These strategies help testers create smart and meaningful test cases without knowing the code inside the software. Next important long question is 4. Strategies and methods for white box test case design. White box testing means testing the internal structure and code of the software. Testers look inside the program, understand the logic, loops, decisions, and then design test cases. It is like checking the engine of a bike, not just riding it. White box testing helps ensure that every line of code works properly and no hidden error remains. 1. Statement coverage. This method checks whether every statement in the code is executed at least once. Example. A is equal to 5. B is equal to 10. C is equal to A plus B. Print C. A single test case is enough to execute all statements. Goal: no line should remain untested. 2. Branch coverage, decision coverage. Every decision, like if-else, must be tested for true and false outcomes. Example. If age 18, print adult. Else, print minor. Test cases. Age is equal to 20 true. Age is equal to 15 false. Goal: all branches should be executed. 3. Condition coverage. Tests each condition inside a decision separately, even if combined with others. Example. If age 18 and citizen is equal to yes. Allow underscore vote. Test conditions independently. Age condition. Citizenship condition. 4. Loop testing. Loops are tested for 0 iterations, 1 iteration, multiple iterations, maximum limit. Example. A loop printing numbers 1 to 10 must be tested for 0, 1 and 10 iterations. 5. Path coverage. Ensures that every possible path in the code is tested. Best for complicated programs with many decisions. Example. If a function has multiple if-else blocks, we check all routes from start to end. 6. Basis path testing. Uses flowcharts to find independent paths in the program. Helps reduce unnecessary test cases while covering all logic. Easy tip to remember: SBCLPB. S. Statement coverage. B. Branch coverage. C. Condition coverage. L. Loop testing. P. Path coverage. B. Basis path testing. White box testing ensures the inside of the software is strong, stable, and error-free, just like a solid foundation of a building. Next important long question is: 5. Discuss about test adequacy criteria in detail. Test adequacy criteria. Test adequacy criteria help us understand whether our testing is enough or not. It answers an important question: have we tested the software properly, or do we need more tests? These criteria act like measuring tools to check the completeness and quality of testing. 1. Requirement coverage. This checks whether all requirements of the software are tested. If a feature is mentioned in the SRS, Software Requirement Specification, it must have at least one test case. Example. If a banking app requires login, balance check, fund transfer, each feature should be tested separately. 2. Code coverage. Used in white box testing. It checks how much of the code is executed during testing. There are different types. Statement coverage, every line is executed. Branch coverage, every decision's true-false path is tested. Path coverage, all possible routes in code are tested. Example. If a function has 20 lines and tests cover only 15 lines, coverage is equal to 75%. 3. Fault detection ability. Adequacy depends on how well tests detect defects. A strong test suite finds more bugs, a weak one finds fewer. Example. If your test cases find issues in the payment gateway before release, that means they are effective. 4. Boundary coverage. Checks if test cases include boundary values. Most bugs occur at limits, so adequate testing should cover. Just below boundary. At the boundary. Just above boundary. Example. Age field, 18 to 60 test 17, 18, 19, 59, 60, 61. 5. Input space coverage. Checks whether enough different input combinations are tested. Not every input can be tested, too many, but all important categories must be tested. Example. For a phone, test different data types. Valid input. Invalid input. Empty input. Why adequacy criteria matter? Ensures complete and meaningful testing. Reduces risk of missing defects. Improves software quality and user trust. Helps decide when to stop testing. Easy tip to remember: RCFBI. R. Requirement coverage. C. Code coverage. F. Fault detection. B. Boundary coverage. I. Input space coverage. These criteria ensure that testing is not random, but smart, complete, and effective. Next important long question is: 6. Evaluating test adequacy criteria. Evaluating test adequacy criteria means checking how well our testing meets the standards we set. It helps us judge if we have tested enough or if more testing is needed. Think of it like evaluating exam preparation. You check if you completed the syllabus, practiced questions, and revised properly. 1. Measuring requirement coverage. We evaluate whether all requirements have test cases and whether those test cases have been executed. How to check? Make a requirements traceability matrix (RTM). Map each requirement test case test result. Example: if a shopping app has 10 features and you tested only 8, your coverage is incomplete. 2. Evaluating code coverage. We see how much of the actual code is executed during testing. Tools like Jacoco, Cobertura, or JUnit reports help measure coverage. Types checked. Statement coverage. Branch coverage. Path coverage. Example: if only 60% of the code is executed, hidden bugs may remain in the untested 40%. 3. Checking fault detection efficiency. This evaluates how effective test cases are at catching defects. How to check? Count number of defects found. Compare with the number of defects expected, historical data. Example: if earlier versions usually had 30 bugs, but you found only 5, your test cases might be weak. 4. Reviewing boundary testing. We check if all important boundary values are covered. Example: for age 18 to 60, ensure you tested 17, 18, 19, 59, 60, 61. If boundary tests are missing, your testing is inadequate. 5. Input space evaluation. We check whether we covered all important types of inputs: valid, invalid, empty, special characters. If certain categories are missing, testing is not considered adequate. Why evaluate adequacy? Helps decide when to stop testing. Ensures no critical areas are missed. Builds confidence in software quality. Reduces risk of post-release failures. Easy tip to remember: RCFBI is equal to evaluate everything. R. Requirements. C. Code. F. Fault detection. B. Boundary. I. Inputs. Evaluating adequacy ensures that testing is complete, meaningful, and reliable, just like checking all items before a journey. Next important long question is: 7. Explain about different levels of testing. Levels of testing. Levels of testing describe how software is tested step by step as it is built. Instead of testing everything at once, testing is done in layers. This helps catch defects early and ensures good quality. There are 4 main levels of testing. 1. Unit testing. This is the first level and is done by developers. Here, individual small pieces of code, like functions or methods, are tested. Purpose: find mistakes early, before combining modules. Example: testing a simple function that calculates the total bill in a shopping app. Tools: JUnit, NUnit, pytest. 2. Integration testing. After units work properly, they are combined to see if they work together. Purpose: check communication between modules. Example: in a banking app. Login module. Account details module. Transaction module. Testing ensures that login correctly connects to account details. Types: Big Bang, Top-down, Bottom-up, Sandwich. 3. System testing. The complete software system is tested as a whole. This is usually done by testers, not developers. Purpose: check whether the entire application meets requirements. Example: testing a railway booking website end-to-end. Login, search, train, select, seat, payment, ticket generation. Types include performance testing, security testing, usability testing, etc. 4. Acceptance testing. This is the final level, done by customers or end users. Purpose: check if the software is ready for real use. Example: a school tests a new attendance management system before fully launching it. Types: UAT, user acceptance testing, alpha testing, beta testing. Why levels of testing are important? Finds defects early, makes software reliable, saves time and cost, ensures customer satisfaction. Easy tip to remember: UISA is equal to Unit Integration System Acceptance. Just like building a house, first test bricks, then rooms, then the whole house, software is also tested layer by layer. Next important long question is: 8 different types of testing. Different types of testing. Software testing can be done in many ways, depending on what we want to check. Each type of testing has a specific purpose to ensure software quality, reliability, and user satisfaction. Here are the main types. 1. Functional testing. Checks if the software works according to requirements. Focuses on inputs and outputs without looking at code. Example: in a mobile banking app, sending money should update the recipient's balance correctly. Subtypes. Smoke testing, basic checks to see if the software runs. Sanity testing, verifies that a small section works after a change. 2. Non-functional testing. Checks how the software works rather than what it does. Focuses on performance, security, usability, etc. Example: a website should load within 2 seconds even with 1000 users. Subtypes. Performance testing, load testing, security testing, usability testing. 3. Manual testing. Testers check the software manually without automation tools. Example: clicking buttons, filling forms, and verifying results on a shopping app. 4. Automated testing. Tests are executed using tools or scripts, useful for repetitive or large tasks. Example: running 1000 login tests automatically with Selenium. 5. Regression testing. Checks whether new changes break existing functionality. Example: after updating a payment feature, ensure balance check still works correctly. 6. Alpha and beta testing. Alpha testing, done by developers or internal testers before release. Beta testing, done by real users in the market before full launch. Example: a new game is tested internally, alpha, and then released to selected users, beta, for feedback. 7. Exploratory testing. Testers explore the software without predefined test cases to find unexpected defects. Example: randomly trying unusual sequences in an app to see if it crashes. Easy tip to remember: FNMARE is equal to fun never makes apps run easy. F. Functional. N. Non-functional. M. Manual. A. Automated. R. Regression. E. Exploratory. These testing types ensure software is bug-free, fast, secure, and user-friendly, just like checking a car for brakes, engine, mileage, and comfort before driving.